Okay, so Fabienne asked me to introduce Reinhard Genzel. Guess that for the vast majority of us it's not necessary, but there are a few young people, so Reinhard is one of the directors of the famous MPE, Max Planck Institute für Extraterrestrial Physics in Galactic. He is also a professor at Berkeley at the Ludwig Maximilian University of Munich. He is a member of many academies of science in the world, including the US National Academy of Science, but also the French Academy of Science. Don't forget that he is one of the Doctor Honoris Causa of the Observatoire de Paris. So the field of astrophysics of Reinhard include many things. Galactic nuclei, ultramassive black hole, star formation, cosmic evolution, and dynamic evolution of galaxies, and many more. He received several prestigious awards, including the Crawford Prize, the Shaw Prize for Astronomy, but of course, above all, he received the Nobel Prize in 2020 jointly with Andrea Guess for the discovery of the supermassive black hole, massive black hole at the center of the Milky Way. I want to add that our team in Asia had the privilege to start collaborating with the Reinhard teams in the 90s, thanks in fact to Pierre Lénard and Reinhard. And so we share a lot of interest, especially about the physics of and the environment of the black hole at the center of the galaxy, and also collaborating in numerous instrumentation that were used for that purpose, in common plus, NACO, and of course now gravity. So right now we have the pleasure and the honor to tell you your talk about the cosmic evolution of star-forming galaxies.
Thank you, Daniel. It's like coming back to one's family. Indeed, Pierre, you started it all. You started it all because you knew early on what the VLT could do. You were the one who convinced everyone to go for this crazy 4x1 arrangement, and not even in a single line, which really made the interferometry then possible. And of course, Michelson had done interferometry in the 1920s, but nobody else after that until Charles Townes really was able to repeat that in a way because of the short wavelength, the high frequency, the short times of coherence and so forth. And so thinking to turn a wonderful VLT into now what is really a breakthrough machine in high resolution milliarc second and astrometric microarc second astronomy seemed a little far-fetched. And when we tried it together, initially we weren't sure we would make it, but it's pretty incredible what has happened. I mean, the instrument as it is now is 1,000 times more sensitive than any interferometry which was done before. I've seen 2 days before I came here, the new detector, Pierre, which Gerd Finger has just finished, the 512 by 512 APD with no noise. So that will be the next breakthrough for the ELTs and the likes. So the sky is the limit if you work hard, and work hard we did together, didn't we? And it was a pleasure and continues to be a pleasure to do so. Now, we'll not talk about the Galactic Center today. I did on Friday and again tomorrow at the Academy. But today I'll talk about one of the other main highlights of the research we've been doing, in fact, doing together, in particular with Françoise, using instruments, pretty much actually the same instruments on the VLT Symphony to do integral field spectroscopy with adaptive optics. So one can resolve in distant galaxies scales of a few kiloparsecs, so subgalactic high redshift work. And likewise, the instrument down below. Now, if you count the antennas, you will find the number 12. Okay, this is a picture from January when antenna number 12 of the IRAM, what used to be Plateau de Bure interferometer and now NOEMA, has started operating, and we've already taken data, beautiful data in a few weeks ago. This is the other pride, which in fact the two communities of France and Germany in particular have brought together and used tremendously. And the science I'll tell you about, in fact, combines in a major way data sets from both of these instruments. So this is research which I would say spanned about a decade of work. Very hard work because you're looking at very far away galaxies, trying to resolve them spectroscopically and in 2 dimensions, and then understand through resolved spectroscopy their dynamics, and do what, of course, local astronomers in local galaxies have done, namely use rotation curves as far away out as you can do to measure the dark matter content empirically, which has not been done at these high redshifts, and then discover new phenomena, which I'll show you, which are not present in local galaxies, owing to the fact that the one, if you like, controlling parameter at high in galaxies is their gas fraction, and with the gas fraction comes a parameter which is called the tumor parameter, which is the largest scale, which is self-gravitating in a rotating system. And that tumor parameter is very large. And therefore, the friction in such a system is very large. And I'll show you what we think is the impact of all of this. Now, the field, of course, started in the 1990s with the Hubble Space Telescope making the first rest frame optical UV imagery of these high redshift systems. And boy, did they look clumpy, asymmetric, and surely not like spiral galaxies of the local universe. So these pictures, and also, of course, the simulations and the knowledge about dark matter merging of halos, very soon formed a generally accepted broader qualitative picture of galaxy evolution and formation, where basically the high gas fraction systems would form little galaxies, which then in the dense early universe would collide very efficiently. And in these collisions, like in mergers in the local universe, then bump together and form starbursts. That was the picture in 2000. Everyone believed in that. And we now know it's sort of right for some systems, but the real story is a different one. And I think I'll try to show you why. The real story is that, as you see on the right side, there is semi-continuous accretion of baryonic gas from the outer scales, halo scale and above actually to the cosmic web, into this innermost regions, where then these processes, which I'll discuss, at subgalactic scales transport gas very efficiently to the inner regions. Now, minor mergers will add to this process in a significant way, but major mergers actually are rare. We now know are not going to be the driver in most of these galaxies. Certainly there will be some, but perhaps at the 25% level or so. over the last 10 years, a number of surveys with the Hubble Space Telescope on the one hand, using basically rest frame, ultraviolet rest frame optical emission to trace the stellar light on the one hand, in various big surveys, the Cosmos surveys, the Candles, 3D HST survey, etc. Then Herschel, with its various surveys looking at the dust emission. And then, as I said, integral field spectroscopy, both on the VLT with Symphony, but then also on the Keck telescope with Mossfire and other instruments, have sort of brought together a picture of the cosmic evolution per cosmic volume element over redshift space of the star formation rate. And on the left picture there, you see the gray points. That is sort of the average picture you get out of this from the review article by Maddow and Dickinson in 2014. So if you look at the shape of this, is that at very high redshift, the level of cosmic star formation rate is relatively low. Systems are small, not many big galaxies. Then they build up fairly quickly to a peak near redshift 1.5 to 2.5, and then a gradual decrease because universe expands, and as we know, it expands, ever faster the later you go. Now, the shape of this curve, as you see, is very much the shape of the upper curve there, this brownish curve, scaled by some factor. That shape is actually a theoretical shape. That is what you would expect if you take the dark matter and calculate this, the fluctuations of the dark matter distribution, and then the distribution of dark matter halos as they grow in the universe through accretion of dark matter material, and then assuming some fraction of the dark matter is in baryons, and then is transported then to the center, and then you get a decent first order agreement between these two curves. Now, this means that gas and dark matter actually somehow are strongly coupled, and the gas, of course, which produces star formation, is not ionized gas. It's molecular gas. We know that. There may be regions where neutral hydrogen gas can form stars, but we are fairly convinced, at least from what we know, it's the molecular gas. And in the right picture, and then also in the inset, you can see from various surveys, both pointed surveys where you pick a galaxy which you have on an optical picture, then you measure, say, CO lines or the dust in a galaxy, and then you convert this into a molecular hydrogen through establishing conversion rates, or you can actually also do this somewhat more cumbersomely, I should say, by actually scanning volumetrically without looking at the optical emission. Pretty much the same result. You can see that the molecular content in blue there in galaxies also increases to a peak, and then at redshift, peaking at redshift 1.5 or so, and then coming down. Now, this whole system, therefore, is a flow system, a baryonic cycle system. Baryons cycle into the galaxy, form stars there at some efficiency. The parameter dependencies we don't know yet, but there's really form stars there. Then the stars, as they come to the end of their lifetimes, explode as supernovae, at least the massive ones, and eject gas again. Well, actually, they don't eject it from the galaxies and the circumgalactic medium, but they eject it into the circumgalactic medium, such that the gas actually returns some gigayears later as sort of a flow of gas. But then there's also black holes in the system. And the black hole density also would trace, as far as we know now, this distribution function on the left side. So black holes, massive black holes at the centers of galaxies, and the galaxies they are hosting these black holes are forming together, growing together, or to first order. I'm always saying to first order, and this is certainly not a one-on-one kind of a situation, but averaged over time, that seems to be the case. And those galaxies, those black holes, when they are in a high state of accretion, then they are things what we call quasars. And their energy production is so high that in principle, they produce enough energy that they can remove a significant fraction of the interstellar material of a galaxy, or prevent new gas from coming into the galaxy. We think that's the latter, which is the more likely situation, because of course, if you're a point mass in the center and you're blowing with a torch into the galaxy, yeah, you can get there and you can get there, but not everywhere. It's much easier to blow into the circumgalactic medium, heat it up, and then you basically get a static atmosphere of hot gas, which then prevents gas from coming through and forming more stars. And so this process, we believe, theoretically as well as observationally, to be sort of the speed limit of how massive galaxies can be. Because these massive black holes seem to be particularly efficient at around the Schechter mass. I'll come to this in a second. Now, looking again on the right side there, these recent observations actually also have given us an empirical hint that at all times throughout this epoch, the atomic gas, which is the gray points in the green line, is dominant, while the molecular gas, which is the blue curve, is subdominant. So it's not, I mean, you hear often in the literature that at high redshift, the interstellar medium is dominated by molecular gas. Well, that's true within galaxies in locally, but not on CGM scales. That's not the case there. It is ionized gas and also atomic gas. So that's broadly speaking the result of many, many surveys which I've indicated there with their names from different groups, including here in France, and of course Herschel. David has worked on this, has had a major impact on this work. So this is the equilibrium picture of the growth of galaxies, which you see up there, where basically you can parameterize then the dark matter accretion rate from simulations. And you see it goes like 1 + e to the 2.3, roughly speaking, and proportional to the halo mass. And then there's 4 factors which are less or equal to 1. And of course, there's the cosmic baryon fraction in there. And then once you have the dark matter accretion rate, the actual star formation rate comes out of this and has various 4 factors. And there's this m dot molecular gas, which is the basically the reservoir of molecular gas in the galaxies. So there's molecular gas coming in, it's being converted, but not all of it is converted. Quite a bit of it is actually present in the galaxy, which is this blue curve on the left side. So all of this is now empirically studied, I would say, to first order. The difficult parts here are various conversion factors, how you can get from CO of various transitions to molecular hydrogen, how you get from dust to that, and so forth, and IMFs, interstellar mass functions, and so forth, are all issues which leave some holes. But broadly speaking, this cycle, the baryon cycle, explanation seems to hold. Now let's go to the galaxies, and here again, work in the 2000s by mainly the Space Telescope, and then also with Herschel, have shown that galaxies, if you plot them as a function of their mass, stellar mass, and star formation rate, do not just randomly populate these planes at different redshifts, where you see redshift 0, then redshift 0.5, 1, and 2 there, but you see basically that there is a prominent sequence, probably near 1 sloped, so a star formation rate proportional approximately to stellar mass of star-forming galaxies. And then below this regions are the passive galaxies, which are, so to speak, those which gave up because they wouldn't be fed anymore. And you see at redshift 2, there are very few of these passive galaxies, but then as you go to the lower universe, ever more galaxies pile up at this passive level. The Milky Way is sort of at the tip of the star-forming sequence in the modern universe. And so we can say that, statistically speaking, it's unlikely that the Milky Way will grow very much, because it will, in fact, pretty soon go into this limit, at least if it accretes, that it would feed its black hole. Is that likely to happen? Probably not, because we are now entering the geriatric phase of the universe, where the accretion rates are low enough that quasars are very, very rare, and typically only happen when you have collisions between galaxies. But the Milky Way at a high redshift would be, in fact, in this situation. So that's the so-called main sequence of star-forming galaxies. And so, again, going back to the 2000s, when this started to get found, people just didn't understand why starburst galaxies, remember the picture I gave you, starburst galaxies, there should be a correlation between stellar mass and star formation rate. Why would you have that? I mean, a starburst galaxy is something where you bang something together and then you get a lot of star formation for a short period of time. Herschel, in fact, has shown that anywhere between redshift 0.5 and 2, only about 10%, say, 5 to 10% of the cosmic star formation rate occurs above this main sequence, above the main sequence where this equilibrium growth picture seems to hold. Whether that story holds up at redshifts higher than 2, we don't know. That's because we haven't had the sensitivity and also the coverage in the infrared to do the same kinds of measurements. That is something which we, of course, eagerly await to see from the James Webb Telescope. Whether perhaps at redshift 6, the universe indeed was much more dominated by starbursts than by this equilibrium. Could very well be, I don't know. I've mentioned already the speed limit, the Schechter mass, which from the measurements we have in this redshift range seems to be always just under 10 to 11 solar masses with a range in stars. So that's the maximum amount, and then there's an exponential fall off. So that's the second ingredient. The third ingredient, and now we come to the measurements, which I wanted to discuss in more detail, is, of course, what kind of objects are these main sequence galaxies? And again, when we started with Symphony in 2005, to look at these high redshift galaxies for the first time. And in 2006, wrote a Nature paper about the first ever high redshift galaxy kinematics with adaptive optics, so resolution of about 2 kiloparsecs. We then said, oh, these are disks. These are rotationally dominated galaxies. Boy, did we get ourselves into trouble. Nobody believed it. Everyone said, oh, well, this is just some shear, velocity shear in mergers and so forth. It took about 5 years until the community came around. Even then, in the 2010 period, the word was, oh, well, some fraction are disks. Now we would say, statistically speaking, that up to a redshift about 2, 2.5, and above a stellar mass of maybe 10 to the 10 solar masses. More than 70% of the galaxies are plausibly disks. Why do I say plausibly? Well, I mean, what is and what is not a disk, you can, of course, get directly out of the kinematics if it's good enough. These spider patterns, as we say, these characteristics, isovelocity contours are very characteristic of a galaxy which is rotating. So that's the statement which I think most people now would accept. There's still some people who don't believe it, but most people would indeed say, yeah, I mean, that's about 70% in this higher mass range between 10 to the 10 and higher. Below 10 to the 10 solar masses, indeed, galaxies have kinematic properties which sometimes are very weird. And that comes about because in addition to the rotational velocity, the large-scale rotational velocity, there's also a small-scale random component of motion. We call that velocity dispersion. Now, we have to be careful with that because we can only call something dispersion, of course, if that is measured on the cloud scale, which none of these observations do. Even the adaptive optics observations don't do that. For that, we will have to wait for another generation of observations, probably until the ELT is gone, although with ERIS, the upgraded symphony and improved adaptive optics, we might now push to maybe a kiloparsec, which is the tumor scale, and that's sort of more sensitive way to probe the kinematics. But at the scale which we can probe, there is a significant component of what looks like random motion, velocity dispersion. At the end of the talk, I will tell you that our data already now show it's not just dispersion. It's actually another very important irregular and regular component, but not rotation. It's radial motion. We'll come back to this at the end of the talk. Okay, so with this in hand, we can try to do what the low redshift community has done profitably, but not without pain. Namely, to ask whether you can use rotation curves, gravity, to probe what's out there in terms of dark matter. And as you know, the story is that these observations, which have been taken over 30 years, say, generally speaking, that for more massive systems, disk systems beyond, say, 10 kiloparsecs, the kinematics is dominated by dark matter. Because the rotation curves are flat and do not fall off like a Keplerian, for instance. So there must be a distributed amount of mass. Or, of course, the force law is wrong. You allow me to not pursue the second thing here. I don't want to, ridicule it, but I think a more likely solution indeed is the dark matter solution, whatever the dark matter then is. And so the question for us is, can we do this at high redshift? And the answer, of course, is a bit complicated. On the one hand, the resolution we have is poor enough that we have only typically between 2 and 6 resolution elements across galaxies. So you might say that's a slim way. Also, we don't have H1. H1, which allows you, at least for some local galaxies, to map out the rotation curve to 50, 60 kiloparsecs. Now, when you go to high redshift, redshift 2, please divide everything by 2, because, of course, the universe is smaller then. So how far do we get out in our observation? Well, typically, if we work hard and integrate for typically, say, somewhere around 20 hours per galaxy, we can get out to about 20 kiloparsecs. So that is the same as 40 kiloparsecs in a modern galaxy. So that's not to sneeze at, but still, you might wonder whether that's not far enough out here. Now, there's a second problem, which is very well known in low redshift analysis of rotation curve, and that's the so-called disk halo conspiracy. As you see in a typical redshift 0 galaxy with about 2% of the mass in baryons in the galaxy, the blue curve, which is the disk, the baryonic component, and the green curve, which is the dark matter, overlaps very significantly over a large part of the measurable range. And so you shift a little bit, the dark matter mass, and you shift a little bit the baryonic mass, and you wouldn't know it in the data. You cannot distinguish. And so you can get very wrong answers from this, and that's, as I said, that's very well known conspiracy. But actually here we are pretty lucky at high redshift in that everything is smaller by a factor of 2, I said already, just because of the expansion of the universe. Also, we know from dark matter simulations that the concentration of dark matter halos is less by about a factor of 2. So that means the galaxies, the baryonic material, tends to be on small scales, more small scales, and the halo on larger scales. So you have more of a separation for the same parameters if you go to redshift 2. So that helps you to be more sensitive. I'm not saying totally sensitive. I'm saying more sensitive to separating dark matter and baryonic matter. And then comes another effect. And that's called asymmetric drift. That's the fact that, as I mentioned already, a significant fraction of the energy of the motions in the galaxy is in a random component. That random component shows up as a pressure in the energy equation, and therefore you have to take that into account. And so if you only look at the rotational motions, if you have a constant velocity dispersion, the rotation curves by themselves drop, just because the random motions become more and more important as you go further out for constant velocity dispersion. So this asymmetric drift component, then if you write it down in equation there on the right side, rotational velocity squared is the circular velocity squared plus this pressure term due to the velocity dispersion, 2 sigma squared, and you write that out. And then you go to the last equation, then you basically see that the rotational velocity squared is proportional to 1 over 1 minus the dark matter fraction within the characteristic radius RE, and then a second term, which is this asymmetric drift term. So if you see a galaxy with an asymmetric drift, so if you see a velocity dispersion dropping, then this second term must be significant relative to the first term. And that immediately tells you that the dark matter fraction cannot be high. So that's very, very important qualitatively. So we have a few actually advantages, if you follow my argument, at high redshift, which at low redshift you don't have. Of course, the velocity dispersion does not need to be constant. So that's a question of whether you can establish that empirically. So what we do is we forward model from a parameterized mass model. So we take a bulge, a disk, plus an NFW halo. Then we convolve that model with the empirical beam resolution, and then we project that model into a 2-dimensional velocity field, and then we extract along the major axis what you would call a rotation curve. You can also model the 2-dimensional velocity field directly, but actually I would argue that the 1-dimensional information is the strongest along the position angle of the kinematic axis. Then you need some priors. You need to know what the inclination of the galaxy is. You need to know what the exponential distribution or otherwise power distribution of the disk is. You need to know what sigma naught is in RE. These quantities we typically extract from HST data. Okay, so they're because they have very high signal noise ratio and high resolution. The parameters on the dark matter concentration we use from simulations. And finally, the bulge to total is something which is can be derived from very good data just from the central behavior of velocity dispersion and mass. Or you again take the HST distribution and then you do a posterior fitting or MC analysis. Now, these kinds of techniques are done by many people. Broadly speaking, a number of people get the same results, but you take different codes which are available in the community, and you will find some differences. So let's be sure that this is something where you have to always be there and be ready to defend your results. So here's one case of a galaxy which, as you see, so there you, on the left side, you see on the upper left, the H alpha distribution. Next comes the velocity field, then comes the velocity dispersion field. And then here the cuts along the major axis of the H alpha distribution, the velocity field, the velocity dispersion field. And there you can see that's a galaxy which clearly has a dropping rotation curve. Where in fact, however, most of that drop is due to asymmetric drift. Okay, so it's not a Keplerian drop. It's due to this fact that the velocity dispersion, if you go to the outer part of the galaxy where there's no beam smeared rotation, you could see that the velocity dispersion in the galaxy is sort of like 60 kilometers per second. So that term 2 sigma squared times R over RE is quite significant. But in any case, from these kinds of data, you can, for such galaxies, for sure, you can get a pretty good analysis of the properties of the galaxy, the baryonic mass, dark matter fraction, etc., etc. Yeah, here are a few more. So over 10 years, we've assembled about 100 such galaxies. And, this is not to laugh at, as Francois can attest. We've had a great deal of trouble convincing panels of telescope assignment to give us this much time, because it cannot be done in an integration of an hour, okay? It cannot be done, even with the best telescopes. Now, you can do this with H alpha, and you can do it with CO. And fortunately, we have a number of cases. I'll show you one particular one a little later, where we can take several traces, as to convince us that, in fact, we're getting pretty much the same result. That's very important. You want to make sure that you're not, so to speak, you're getting fooled by some particular idiosyncrasy of one tracer. But the so-called RC100 sample we now have assembled is the equivalent of 1,200 hours of integration on the VLT, NOEMA, and LBT. So that's a gigantic amount of telescope time we have assigned to this, hopefully with good reason. So what do we find? Well, first thing you can immediately say, let's plot what most people would immediately plot, namely the dark matter fraction at a given redshift as a function of VC. You do that because it's known from local observations that there is a trend for the low mass galaxies to have high dark matter fractions. And the dwarf galaxies, of course, are totally dominated by dark matter, even in their cores. And for the higher mass galaxies, to have somewhat lower dark matter fractions. The Milky Way there is this red square, and you see it's about 40% with some error. There's a term which you find in the literature, which is called maximal disk. So that's sort of the transition between what people would call a totally baryonically dominated disk and one with a substantial amount of dark matter in their outer disk parts. And the Milky Way sort of sits at that border. There's no consensus in the literature where exactly the Milky Way is. But this trend is very clear. Now the trend and the numbers depend very much on the initial mass function. So this arrow there denotes if you make a difference between a saltpeter IMF, which would be the bottom part of the arrow, and a Chabrier IMF, which would be upper part. And as you know, this is a, if not an unknown, it's at least a variable which people are talking about a lot, and whether that might change as a function of mass. So that's the redshift zero situation, and the answer is at the massive end, so that would be around 300 kilometers per second, just the most massive systems before they turn into ellipticals. They are barely baryonically dominated. Everything else at a low redshift is dark matter dominated. Now let's go to redshift 0.6 to 1.2. So we're slicing our sample into two redshift slices of equal time content, 0.6 to 1.2 and 1.2 to 2.5. So now you see these blue points are the individual data measurements. And you see at low mass, we are still, broadly speaking, seeing the same thing as the redshift zero results. But at high redshift, we're seeing more, significantly more objects which have very low dark matter fraction. But still, on average, which is the cyan square there, we're still sitting on the same kind of a distribution. So there's a change there, but it's not dramatic. It becomes, however, very dramatic at redshift 2. Here you see, not only do you see a lot of galaxies which are massive and have low dark matter content, but you also see lower mass galaxies which have low dark matter content, very low. In fact, some consistent with zero. Some consistent with zero. So clearly that is very surprising. Or is it? Or is it? Well, actually, it may not be, because you see in the upper right, there I plot, in addition to the disks, the triangles, passive galaxies from the Atlas observations, passive elliptical galaxies. And okay, again, depending on the IMF and so forth, but for a saltpeter IMF, the passive galaxies at low redshift all have low dark matter content. In fact, if you plot that curve, which goes through that down below, then it's pretty much what we see. And indeed, those galaxies up there are the descendants of the high redshift star formers, right? Because the star formers stop star forming at some point thereafter, and then they turn into these elliptical type galaxies. So it seems that we have a process which, in particular at the peak of the cosmic star formation rate at redshift 2, has galaxies with a low dark matter content. And the question now is, if you were convinced that this is empirically now halfway persuasively established, what is the reason? Now then you look for various correlations. Well, okay, I've lost one slide, but let me say the strongest correlation, in fact, is with the density, the surface density of baryonic matter. So high surface density objects have low fractional dark matter. Now you say, oh, well, that's trivial. If you make a small object like a bulge, that definitely has a low dark matter fraction. But no, these objects which we're looking here, in fact, we are biased in the size distribution. We're picking up really big objects because we want to resolve them in their resolution. So when I say dense objects, dense and large. So that's not the same as the very small nugget of baryonic matter. Another way of expressing the finding is in this way. Okay, so here we have the baryonic surface density down below versus the dark matter surface density. And now the dark matter surface density you can compute in various ways. One, and that is the green green bar there from an NFW, Navarro Frank White distribution, given a certain baryonic mass. That's the classic way to calculate via a scaling relationship the dark matter content of the entire galaxy, and then also within RE, which is what this is. And then you get this green distribution, which is a very shallow distribution. So the NFW prediction is that it doesn't really matter what you do, is most of these galaxies have a few by 10 to the 8 solar masses per kiloparsec squared dark matter density. Now the observations don't show that. In particular, the red points, which are the redshift 2 points, again. The blue ones are the lower redshift points. Well, they cluster more up there. But the redshift 2 points are really, really don't agree with that statement. They are missing dark matter in their cores within RE by some factor of 10. The interpretation we have for that is that there is a process on subgalactic scale which removes dark matter in the process of the formation of the galaxy. And basically, the idea is as follows. The NFW profile, you may recall, has a cusp. And if you calculate the temperature of the dark matter, then it has a minimum in the center. So it's a cold dark matter distribution. If you now bring in baryons from the outside through processes which I'll discuss, then you will heat up the cusp. If you then, in addition, energize this system through feedback, either stellar or black hole feedback, then you can remove dark matter from the center and baryons, by the way. That's, in fact, general wisdom amongst the simulator community that you can do that. I would argue that we see this here in great style done in galaxies of the early universe because the processes of radial bringing in material are so large, as I will explain to you now next. However, let me now talk a little bit about these velocity dispersions. So what we do, as I mentioned, we are fitting a constant velocity dispersion to each and every galaxy, and then we can establish, say, in ionized gas, the median values of the ionized velocity dispersion as a function of redshift from our RC100. And you see there is a small amount of increase to high redshift, but compared to low redshift, that is very substantial. The low redshift point is down at 1. So as we go from low redshift to high redshift, the velocity dispersions increase by, say, a factor of 3 or 4. And they increase approximately the same in the molecular gas, which are the black squares, as in the ionized gas. But I don't want to, go on to war on this. I mean, there can be small differences, but they are not huge. So it's a property of the interstellar medium at high redshift that these dispersions are larger than at low redshift. And this is not just finding from our surveys. There are many other surveys from the literature which basically show the same thing. So velocity dispersion, as you go back in time, increased by some significant factor of 3 to 4 to 10 gigayears before our current time. So now what about this velocity dispersion? If you look at a gas-rich disk, and you look at the equation of instability, gravitational instability with rotation, then you have this dispersion relationship down there, omega squared equals and so forth. And so if you are unstable, then this omega squared has to be less than 0. And that gives you a relationship between V rod, sigma, and SCS. And so that gives you a cascade of instability from the smallest scale, which is unstable, which is the gene's length, to the largest scale, which is the tumor length, which you see there. And that tumor length is proportional to the tumor parameter, equivalent to V rod over R squared. And if you express that a little differently, then you get it in terms of this key equation there. Sigma over V is proportional to F gas over, say, square root of 3 or square root of 2 times Q. Q in marginal instability is 1. So you would get the larger the gas fraction, the larger sigma. That's the essence of this simple model. Now, this is a linear model. At high redshift, when we look at these galaxies, well, they actually have formed stars already. So it's not anymore in a linear instability state. So actually, the empirically calculated Qs are a little less than 1.5. So, but the main thing is sigma over V is proportional to gas fraction. And I've shown you, or I've told you, that the gas fractions of these early galaxies are significantly larger than the ones in the local universe. So you would expect from this tumor argument them to have larger velocity dispersions. So once you have that, then any transport time scale inward, either through dynamical friction or viscous process, go like V over sigma squared times the dynamical time scale times the force factor. So V over sigma squared, sigma over V in the modern galaxy, or V over sigma in the Milky Way is about 15 to 20, and at high redshift it's about 5. So that's a factor of 4 difference, squared out 16 times. So that means at high redshift, these transport scales, which transport material through dynamical friction and or viscous effects, are 15, 20 times shorter than at low redshift. And that number is typically a few 100 million years. So within a few 100 million years, you can actually transport through this effect big amounts of material into the centers. I should say that this effect was presaged in many ways by 3 famous theoretical papers by Noguchi, Imeli, Gerhard, and then Bono, all finding the same thing, the content I've given you. And so you start with one of these clumpy galaxies. The clump size is proportional to tumor scale, which is also proportional to the gas fraction. So they're very large at high redshift. Therefore, the dynamical friction becomes very large. And you see very quickly you transport gases. So that's the general idea of this. Well, let me actually leave that aside. We can come back to this if you want. I want to go directly to this slide and basically say now, if we look at the velocity dispersion as a function of star formation rate in different galaxies empirically, then you see what I told you all along is that in low redshift universe, interstellar medium is relatively quiescent. It's typically 10 kilometers per second on large scales. But then as we go to high redshift, it increases. So in the low redshift universe, the narrative has always been that this steering up of the interstellar medium is due to feedback. Supernovae, stellar winds, etc. If you look at the equations in more detail, that was done first by E. Ostreicher in 2009, and then in a very nice paper by Mark Krummels in 2018. I highly recommend that paper. You find that the theory of this effect would predict a constant velocity dispersion. So you can pump any amount of star formation rate up. You will not increase the velocity dispersion of the layer. You will just increase the thickness of the layer. Okay. Only if you include the gravitational instability theory, which I added to you, then you get this red curve. So you go from a feedback dominated interstellar medium on the left side, which we have probably in the local universe, to a gravity dominated universe on the right side. And then you can understand these very large loss dispersions in the way I've explained to you. Okay, let me come to one last and very recent progress in this regard. Can we see these radial motions? Okay, we have a prediction. We actually have a fairly clear prediction of the magnitude. The magnitude of these radial velocities is on the order of sigma over v times sigma times 4 factors. So that's somewhere between, in the end, somewhere between 30 and 80 kilometers per second, depending on the case. That's prediction by theory. The question is, do we have good enough data to show that? And here's our star, BX610. It's one of our very nice, beautiful star-forming galaxies on the main sequence. In fact, it's a little below the main sequence. It has, as you see in this 3-color optical picture on the left side, it's about a pretty face-on system, 39 degrees at redshift 2.2. It has a significant bulge. And then you have, sort of a bit of a bar-like structure going in this direction, and then this rotating, this beautiful rotation. When you look at the velocity in CO with ALMA, by the way, this is a 24-hour integration with ALMA. It's the longest integration ever done with ALMA. This is something which Francois and we have tried for years, and we were not given it. But we managed to get one because one of our collaborators is Chilean. So you see clearly a beautiful rotation pattern. The same rotation pattern you see on the right of it, that's H alpha. Then you go to H alpha and adaptive optics, right of that. Pretty good too. You can even go to nitrogen 2, see the same thing. So now we make our model, which I have described to you. We make a forward model of the mass and kinematic model of this galaxy. Subtract then the model and look what the residuals are. And that's the answer. In the upper line in velocity and in the bottom line, the velocity dispersion. Now you see, in all 4 species, the same effect is there. The galaxy in residuals has a blue to reddish gradient from the northeast to beyond the center in all 3. So look at the component which is comparable, slightly different, but roughly comparable. Interestingly, also the velocity dispersion also shows a similar kind of a pattern. Maybe you don't see that so easily. That at the nucleus, which is this region here, there's sort of a minimum. And then there's sort of a ring of higher velocity dispersion. Okay, so now let's make a mock galaxy with a, oh, I'm afraid. This is not on this, or is it? Well, anyhow, if you extract the parameters through the model, you infer, if this is an in-plane motion, that this must be an inflow at about 95 kilometers per second. And that's in fact exactly what you would expect from the theoretical curves. So the theoretical prediction is V in is sigma squared over VC, as I mentioned, with 4 factors, which in the case of BX610 would come out to be about 95 kilometers per second. So that's the case I explained to you. Now, some detail there, BX610, but we have a few more. So if I divide the data V in by the model V in from such an inflow, you're near 1 for quite a number of cases. I think we still have a way to go, and we'll have to work hard on this. But I think we've shown now that, in fact, these inflows, this inflow theory of gravitationally unstable disks, indeed is the culprit, which generates dispersions and at the same time drives gas at a very large rate inwards, which then in turn lowers the fraction, the dark matter fraction in their centers, and produces baryonically dominated galaxies. Just to show you a mock data of EX610. So you set up a rotating galaxy plus such a inflow, but not an inflow from all sides, but along a line. And velocity residuals are on the top, and the velocity dispersion on the bottom. See the same kind of features. Now I know that Francois will tell me a bar flow does not produce a blue-red. Yeah, we have to understand that. But that's what we put in. An inflow along a linear structure, a bar, and that generates the right kind of patterns, which we've seen in the data. Okay, so what I've told you is that we've made a lot of progress in high redshift. We understand that these clumpy asymmetric thingies are likely not very rarely starburst galaxies, but actually galaxies which are in a somewhat equilibrium state with excursions, of course, and minor mergers and all the rest of it. But the clumpiness is a property of their gravitational instability throughout at large gas fractions. That makes these beautiful big clumps. And depending on which clump is brightest in the UV on Fridays, gives you and then the impression on the HST image, okay, which then can look very asymmetric. If you look at the kinematics on the other hand, the kinematics can be very symmetric. And these accretion rates inwards are initially very large, then lead to large star formation rates in tumorally unstable disks, so that the clumps, in fact, are the locations of the minima in Q. And then they also produce outflows. We see these outflows. I have not today talked about those in ionized and molecular gas. And then they lead to radial transport of gas, forming compact bulges very rapidly, and probably, I argue, remove sufficiently large amounts of dark matter into the galaxies. And this goes as long as the galaxy actually has sufficient transport at high redshift of gas inward, and that happens until you reach roughly the Schechter scale. Right, so that's what I wanted to tell you about our work on early star forming disks. Thank you.
I suppose that you have question. If it's not too difficult, can you come to the microphone? Because we are broadcasting. It will be better for the quality. So, François, of course. With this one.
Okay. So
no, it's okay.
Thank you very much, Reinhard. It was a beautiful and very, very beautiful results, and high redshift, very, very interesting. So I agree with you for most of them, what you've said, maybe not the last ones, because I saw a very neat bar in your B610, and I think that indeed you are seeing elliptical streamline as usual, and in fact, it's much better because if you think that it is only radial motion, in very short time, you will have a big bulge. And in many of these galaxies, you will have difficulty to find less bulge at the end, because you know that most spiral galaxies nowadays have no bulge. So it would be very difficult if you form bulge so quickly. So maybe you have...
You know what, most galaxies probably could have formed at a later time. I certainly make the case that this extreme fast inflow of material and bulge bulging is a strong function of cosmic time. And so only galaxies which started early enough will be part of that.
But you think that all the galaxies Z equal to that you showed Earth was not ours today? There were
very far-reaching conclusion, which
because in fact I agree that the galaxies are more clumpy, and there are more. There's more friction and viscosity, but not as high as you assume that all is random. In fact, when you look at your velocity field, they're very regular. They are very in rotation. They are coherent. They are not really completely random. So you'll not see the.
Yes, we do. I mean, the galaxy which I showed, the ratio of the radial velocity.
Yes, but to see a radial motion, it is more difficult than it is completely random. You will see random motion when there is a bar, and indeed a coherent one. But if it is radial motion due to random motions, you will not see it. You know what I mean?
I'm a very simple observer. I observe a radial motion going into the center, whose magnitude is a third of the rotation.
Yes, but in a bar you have molecular gas in one side and the other, in the two, so that you see an elliptical streamline only blue and red.
Yeah, but I mean, on the other hand, you see, you're starting from a picture of stellar dynamics, right? Which is dominating. Here, it's the gas which is dominating.
Yes, I know, but well, even if you have 50% of gas, you will have this
65% gas at galaxy. So, but okay, we've got to work that out. You're the expert, so.
Like with 65%, you have a very thick disk, and random motion, you have not so coherent radial, which could be due to a bar. But anyway, we will let you all.
D'autres questions? Oui, Xavier.
So it's just to get a clarification on the dark matter possibly being removed from the galaxy. So when you were speaking about the fraction of dark matter, it is within the effective radius. And so as you know, galaxies have reasons to be more compact. And for example, the mechanism you were explaining that bring very efficiently the baryons in the center. And I wanted to ask you whether you think that this would be enough, the fact that you have some compaction mechanisms that bring baryons in the center, or do you also need, as you said, the dark matter, or said otherwise, if you were to see, but we cannot yet, but at larger scales than the effective radius, do you think you would find back your baryons and have the same ratio as simulations?
Very good question. I think now you brought in that word compaction. So there's, Avishai Dekar speak. So Avishai, of course, likes this. And Avishai would argue, before this process starts, the system was dark matter dominated. So in fact, that makes sense, because as we see at the low mass end, the galaxies are dark matter dominated. The dark matter came first, so to speak. Now you start these processes, and then you go through this, at least for those galaxies which happen to grow during that phase, there's a tremendous inflow of flow rates, plus streams and minor mergers. I mean, I don't want to belittle this, okay? I cannot distinguish a infalling clump from a satellite galaxy. I mean, you cannot. We have to wait for the ELT for that. But I mean, broadly speaking, yes, I would say you start with a dark matter-dominated galaxy. And apparently, during this particular phase, you bring in enough energy that you heat up that central spike, remove the cusp, and replace it in the end with a bulge. Part of the bulge, by the way, cosmos will be ejected too, right? I mean, it's not that the baryons escape these processes either.
The stars cannot escape.
No, but they are high fractions of, I mean, if you're measuring this BX610, the gas fractions, they stay high. So the central bulge is not a red bulge. It's a wet, in Abishai speak, it's a wet bulge.
J'en posais une naive question. Naive question. Are there examples of local universe galaxies with decreasing velocity curve where you can test more detail, would say, the effect of dispersion, velocity dispersion, and so on?
Yeah, some people believe they can. Group in Australia has tried that. Blaise Brooks' team has tried that to look for galaxies which have high gas fractions. I mean, this is what you need. And I'm afraid I would have to argue that what you find, if you do that, you find mergers. Because that we know. I mean, mergers also bring in a lot of gas into the central region. So if you then trigger on gas fraction, you will find modest mass mergers. And then the equilibrium aspect is gone. So I'm not convinced, but certainly the case was made that you could use nearbyness to get more detail. Yeah.
No more questions? Oh, okay.
Another naive question. Do we know enough of the history of the Milky Way to see how it fits in this global picture?
Well, the Milky Way at that time had a mass of just over 10 to the 9 solar masses. So it did not figure into this.
Tiny thing.
It was a baby which did not yet experience these kinds of stories. So I'm afraid if you look at the current star-forming population, they were all in this lower mass range. In fact, again, there is definitely a riddle on the lower mass end, which we have not even begun to solve, which in Avishai Dekel's terms are the pre-compaction objects, which are dark matter dominated and probably not rotating. Okay, so these are systems which are in the simulations, for instance. You really believe the simulations in detail. They are rather, distortion dominated, yet highly dissipative, because of course you have a gaseous system. We have not tried to go there because these objects are small and the resolution of the current telescope is still not good enough. But again, the new generation will have an ELV and then they can get at that problem. Yes.
Okay, so thank you again, Reinhard.